Hello and welcome to this video lesson on redox reactions. It has specification reference 3.1.7. As usual, let's start with our learning objectives for this video lesson. The first of which is that we want to know that oxidation is the process of electron loss, and oxidization agents are electron acceptors. Corollary of those two are the next two, so that reduction is the process of electron gain and reducing agents are electron donors. We also want to know the rules for assigning the oxidation state of an element in a compound or ion from the formula. So we'll go through those rules, and we will also be able to, at the end of this video lesson, work out the oxidation state of an element in a compound or an ion from the formula. So first of all, what are redox reactions? Well, redox reaction is a reaction where both reduction and oxidation occurs simultaneously by transfer of electrons. And in order to understand that, we need to go through some keywords. So oxidation, you may remember from GCSE, is the loss of electrons, whereas reduction is the gain of electrons. And in case you've forgotten that mnemonic to help you remember, oil rig, oxidation is loss, reduction is gain. So that means an oxidizing agent accepts electrons but gets reduced itself. So accepts electrons, gets reduced itself. Whereas a reducing agent donates electrons and gets oxidized. Okay, in order to make sure we're familiar with all those words, let's look at a simple example. Let's look at the example of sodium reacting with chlorine. So if we've got a sodium atom reacting with a chlorine atom, or half a chlorine molecule, they're going to form the ionic sodium chloride, where in the ion sodium is positive and chloride is the negative one. And so what we can clearly see is that sodium is losing an electron. It's donating its outer electron. So that makes it the reducing agent. It's donated its outer electron and it gets oxidized. Okay, so that's what happens to sodium. And the chlorine, on the other hand, accepts the electron. So chlorine is the oxidizing agent. And of course it is reduced. Because it has gained electrons. And the electron transfer has gone from the sodium to the chloride. So that's the basics of redox reactions. that would be just a little reminder of what you found out at GCSE level. But there's lots more to redox reactions, and we're going to delve into that now. So now what we're going to do is we're going to go over some rules that are going to help us work out what the oxidation states of various elements, ions, are. And simply the oxidation state, by definition, is the number of electrons that the particle has either lost or gained. So then it's the number of electrons that the particle has either lost or gained. That gives you the oxidation state. So obviously if it's gained, it's going to be minus, and if it's lost, it's going to be positive, because an electron has a negative charge. Okay, when we're working out oxidation states, it's very useful to keep in mind the concept of electronegativity. And because of that, I've got this chart off the internet for you, and it looks like a periodic table. The elements are arranged as they are in the periodic table, but the numbers here are Pauling's scale of electronegativity. So if I can direct your attention to the top right hand corner, for example, with fluorine, we all know that fluorine is the most electronegative element, and there it is with a Pauling scale value of 4.0. And then the second most electronegative element you can see is oxygen at 3.5. And it's color coded such that yellows are medium electronegativity, and then the green ones, or the metals, are less electronegative. In fact, quite electropositive when you get down to the left hand side, especially at the bottom. So you can see the least the least electronegative elements, rubidium and cesium, have values less than 1, for example. Okay, so that's our Pauling's electronegativity scale. We're going to refer to that when we develop about 6 or 7 rules to help you work out what oxidation state a particular particle is. So the first rule, simple one, is for uncombined elements. So uncombined elements. So uncombined elements, for example, silver, for example, oxygen, oxygen exists as a molecule, for example, xenon, and another molecule, hydrogen, exists as a molecule. So uncombined elements are always oxidation number 0. They've not transferred or gained any electrons. So that's clear for a single atom like silver or xenon. Slightly less clear maybe for a diatomic molecule of an element like oxygen or hydrogen. So when an atom is combined to itself, to another identical atom, then we assume that no electron has been transferred. They're equally sharing the electrons in the covalent bonds, and so we can keep their oxidation states at 0. Okay, so that's the first little rule. Second one, let's do monatomic ions. So mono means one, of course, so monatomic ions are just ions on their own. So examples might be a sodium ion or a magnesium ion or a fluoride ion. And for these, the oxidation state is just the charge on the ion. So the oxidation state of sodium is going to be +1. For magnesium, it's going to be +2. And for fluorine, of course, it's going to be -1. And notice the pluses and the numbers are written the opposite way round compared to the way that you notate the ion itself. And that's quite simple, and if you're in any doubt, then you can use the group of the periodic table the element comes from. So for example, oxygen is in group 6, right? So you know that group 6 elements, they want 2 more electrons. So if they were ions, if there was a group 6 element that was an ion, it's very likely that it would have gained 2 electrons, and therefore its oxidation state or oxidation number would be -2. So that's monatomic ions. Let's move on now to neutral compounds. So let's use methane as an example. So methane, you know, is carbon with 4 hydrogens. And here's where we need to refer to the electronegativity chart. Because which one out of carbon and hydrogen is going to be the electron acceptor, and which one is going to be the electron donor? That's the question. Because what we've got here is we've got 4 covalent bonds where carbon is sharing its electron with one of the hydrogens in each case. But for the sake of oxidation states and oxidation numbers, we're going to assume that these bonds are actually ionic, so that we can give some oxidation numbers to both carbon and hydrogen. So if they were ionic, which out of carbon and hydrogen would take the electrons? Because carbon, for example, can either lose 4 electrons or gain 4 electrons because it's in group 4. That's where we need to look at the electronegativity table, and you see that carbon is there at 2.5 and hydrogen is here at 2.1. So carbon, you can see, is more electronegative than hydrogen. So what we do is we say that carbon has taken those electrons in the covalent bonds, and so the oxidation number of the carbon is said to be -4. And because hydrogen has the lowest electronegativity out of hydrogen and carbon, it's assumed to have given up its electron to carbon, and so its oxidation state is given as +1 in this case. So what you can clearly see overall is that you've got 1 carbon at -4 and you've got 4 hydrogens at +1. So overall the methane has an oxidation state of 0, and that's implied by the name neutral compounds. So overall it's 0, but within the molecule or the compound we've given carbon an oxidation state of -4 because it's the most electronegative of the 2, and we've given hydrogen the oxidation state of +1 because it's the least electronegative of the 2. Okay, so that was the first 3 rules. Let's move on to a spare sheet to look at the next couple of rules. So let's deal with rule 4 and 5 together. And so we're going to talk about compound ions, and combined oxygen. So let's use an example to illustrate that. Let's use the sulfate ion that you'll be familiar with from sulfuric acid, for example. So sulfate ion is SO4, and so we're going to have supposed to be okay. Okay, so we've got 4 oxygens joined to 1 sulfur, and overall the ion, as you will know or could refer to your data sheet for, has a charge of 2-. And let me just write here the formula of sulfuric acid for you, just so that it helps you to remember that. So sulfuric acid, you'll remember, is H2SO4. Hydrogen, you know, is going to be +1. Right? Overall, the thing is neutral, but you've got 2 hydrogens, so that's 2 positive charges that are going to be from the hydrogen. So that means that the sulfate is going to be 2-. That's how you remember it. Put a little ×2 in there for you. Okay, so the sulfate ion on its own is a 2- ion. So the oxidation number of a combined ion is the charge on the ion. So the oxidation number is 0 is -2 for the sulfate ion SO4. But within that molecule, we've got sulfur and we've got oxygen. So what we're going to have to do is we're going to have to refer again to our electronegativity table, and we can find oxygen and we can find sulfur. So oxygen is electronegativity of 3.5 and sulfur is electronegativity of 2.5. So oxygen clearly is more electronegative than sulfur. So oxygen is going to be our negative number, and sulfur is going to be our positive number. So let's start with oxygen. Our oxygen is in group 6. It's very electronegative, so it's going to grab 2 electrons to give it a 2- charge. So the oxidation state of oxygen is -2. And that's nearly always the case for combined oxygen, unless it's either in a peroxide, which we'll deal with later, or combined with fluorine, then it's always -2. So if oxygen is -2, and we have 4 of them, the total negative charges accumulated by the oxygens is going to be -8. And the sulfur has got to provide those electrons. So how many of the electrons has it provided? Well, it's provided 6 of those 8 negative charges, because 2 of them are still outstanding on the charge of the ion. So that leaves sulfur as +6. So I'm just going to go over that for you again. You've got sulfur at +6, and you've got 4 of the oxygens each at -2. So you've got +6 plus 4 times -2 equals the overall charge on the ion, which is 2-, and that works out. You can see that that works out as +6 minus 8 equals -2. So you can see that makes sense. So let's go through the last couple of rules for oxidation states, and you heard me mention peroxide. So rule number 6 is about the oxygen exception. So let's say exception to the combined oxygen rule. Right, so the combined oxygen rule is that oxygen is always -2 when it's combined, except when it's not. And the example that we're going to use is hydrogen peroxide. And so let's draw ourselves a molecule of hydrogen peroxide. We've got 2 oxygen molecules combined with two hydrogens. And hydrogen has only one electron. We know that, don't we? So the oxidation number of this is obviously it's going to give it up because oxygen is very electronegative. So the oxidation number of the hydrogen is going to be +1. And this hydrogen is going to be +1 as well. And we know that overall, so overall, let me just try and draw a bracket. So overall, the oxidation number is 0. And so let's draw that out as a formula. So for hydrogen, for the two hydrogens plus the two oxygens, it's all got to be 0. I'll put a stroke through the 0 to make it different from an O. Okay, so for hydrogen, we've got 2 times +1. And for oxygen, we've got 2 times something we don't know yet. So I'll draw a little box. And we know that they've got to be equal to 0. So you can quickly see that the number in the box has got to be -1 because you've got +2 -2 equals 0. So the oxidation number of the oxygens is -1 in the case of hydrogen peroxide. So that's the exception to the rule for combined oxygen. There's one other rule, and that's to do with hydrogen. So hydrogen is it's got one electron. So it's got one electron to give up, and it's got then it will of course have no electrons, or it can gain an electron and have a full 1s orbital. Okay, so what it does depends on what the other element is. So let's assume the other element is fluorine. So with fluorine, and I've picked that because it's very electronegative, the compound is going to be hydrogen fluoride. And fluorine is always going to be -1. There's nothing that can take an electron. There's nothing reasonable that can take an electron off fluorine. No element anyway. And if the whole thing is going to be neutral, which it is, that means that hydrogen is going to be +1. So it's given up its electron to fluorine. Not really very surprising. And that's what happens there. But with group 1 metals, it can form metal hydrides. So let's use the example of sodium hydride. That's NaH, sodium hydride. So sodium, of course, is very electropositive. It's got very little electronegativity, and so that is going to be our +1. If you refer back to your electronegativity table, then the electronegativity of sodium is less than 1, and the electronegativity of hydrogen, I seem to remember, is 2.1. All right, so sodium is going to give up its electron to hydrogen. Hydrogen is the most electronegative of those two, which means in the case of metal hydrides, like sodium hydride, the hydrogen is going to be -1. Okay, and so now you have all 7 rules for the oxidation states. But what I think we'll do, just to cement all this in your understanding, is we'll go through a few examples that you might come across in an exam. So in your exam, you may get a question asking you to work out the oxidation state of one element in a compound. So let's do that sort of example here. Let's say you've got to find the oxidation state of zinc in zinc hydroxide. So you're given the formula of zinc hydroxide, which is that, and it's asked you to find the formula of zinc within the zinc hydroxide. And so it's okay. We're just going to follow the same rules as that we've been through already, and then we'll be fine. So the first thing to notice is that this is a neutral compound. So the overall oxidation state is 0. And next thing to notice is, we'll do this the long-winded way. There's a quicker way that I'll maybe dip into at the end. But the thorough way is to then notice that oxygen is going to be -2, right? Whereas hydrogen is going to be +1. They're normal oxidation states. So if that's the case, then let's now work out what the OH2 bit is, the oxidation state of that. So oxygen is going to be -2, whereas hydrogen is going to be +1. So one hydroxide ion and one OH is going to be -1. So the oxidation state of OH2 is going to be -2. Do we get that? Hopefully you do. So then the oxidation state of zinc can be formed from the fact that the overall oxidation state is 0. So if we just remind ourselves of the formula, zinc hydroxide, and we've just worked out that this bit is -2. We know that the whole thing, let's write it like this, the whole thing is 0, so that means this bit must be +2, and that's the answer. Oxidation state of zinc in zinc hydroxide is +2. Now, just a slightly quicker way of doing that would be to remember that hydroxide is a -1 ion. So the hydroxide ion, you'll have seen written like that many times, and that's got an oxidation state of -1. And if you had 2 of them, then it would be -2, obviously. So you can remember that from like sodium hydroxide. So sodium hydroxide, you'll have seen that written dozens of times. You know that sodium is a 1+ ion, and you know that hydroxide is a 1- ion. So we could have just skipped a step, but it was useful to do it the long way anyway. Okay, so the examples in the exam are not going to be much more difficult than that, and we'll do some practice in class as well. Okay, lastly, let's have a look at systematic names and how that interacts with oxidation states. So in this context, what we mean when we're talking about systematic names is the Roman numerals. Is the Roman numerals used to give the oxidation states of some of the elements in compounds. And it's 4 elements that can have several, at least more than one, several oxidation states. Usually transition metals or sulfur or something like that. So I thought we would start with a table here to give a few examples, a few common examples. So you might come across, when you're looking at a box of, or a bottle of stuff, you might come across something called iron 2 sulfate, and you notice the Roman numerals for 2 in the iron 2 sulfate. And what that tells you is that the iron, the Fe, has an oxidation state of 2. Oxidation state of 2, whereas in iron 3 sulfate the ion is going to have an oxidation state of 3. So in the case of iron 2 sulfate, the formula is sulfate ion SO4 is going to be a 2- ion, so the formula is going to be FeSO4. So this is going to be the 2+ ion, and that's a 2- ion, like that. Whereas if the ion was of oxidation state 3, the sulfate ion can't be, the sulfate ion rather is still 2-, so the formula is going to need to be Fe2, and then we have to put the SO4 in brackets because we need 3 of those. So the charge on these two 3+ ions is going to be +6. Now that's not the charge on one of them, of course, that's the charge on the two 3+ ions, and the charge on 3 2- ions is 6-. Right, so that's 3 times -2, and this of course here is your 2 times 3+. That's where they've come from. Okay, so our sulfate ions, so look here on the 3rd row of the table, we've got sulfate 6 ions. And when a compound has 8 in it, like these 3 have, we've got sulfate 6, sulfate 4 and nitrate 3. The 8 bit, you might remember, means that there's oxygen involved in the ion. So it's going to be a compound ion with oxygen in it, and a sulfate ion is going to have sulfur and oxygen in it. And the sulfate 6, the Roman 6, refers to the oxidation state of the sulfur, because the oxygen always has an oxidation state of -2, apart from those 2 exceptions we've been through. So we're talking about the oxidation state of sulfur, and that's going to have an oxidation state of +6. So the sulfate 6 ion looks like this: SO4 2-. This would be the one that the sulfate ion that we're familiar with. So this is going to be 4 times oxygens, nearly always 2 -2, so that would be -8, which means this needs to be 6+, because we've got an overall charge on the ion of 2-. So by the same token, the sulfate 4 ion is going to have a sulfur atom in it with a 4+ charge on it, or a +4 charge on it. So in which case this is going to be the SO3 ion. It's also 2-. So we can just work that out in the same way. So oxygen is going to be 2-, -2. So, but we've only got 3 of them this time. So it's going to be 3 times -2. So that's -6. We've got overall charge of 2-, so we only need 4+ to be accounted for by the sulfur. And lastly, in the nitrate 3 ions, the nitrogen, according to the Roman 3, is going to have a +3 charge. I should have written all these with the plus in front. So nitrate ion is going to be NO2 with 1-. So you might be familiar with the nitrate ion in, for example, nitric acid, which is NO3 1-, but this is nitrate 3, which is the unusual one, like this one. Okay, so again we've got oxygen, which is -2. We've got 2 of them, so 2 times -2 is -4. And we've got the overall charge on the ion is -1, so we just need +3 for the nitrogen atom in the nitrate 3 ion. Okay, so hopefully that's clear. If not, see me in class, and anyway we'll practice lots of examples in due course. But before we finish with this video lesson, let's just make sure we've covered off all our learning objectives. If you remember, the first one was we wanted to know that oxidation is the process of electron loss. Let's give ourselves a tick for that. I think we know that. And oxidizing agents are electron acceptors. And corollary of those two is that reduction is the process of electron gain. Yep. And reducing agents are electron donors. We've got all those. And then we went through the rules for assigning oxidation state of an element in a compound or an ion from the formula. We went through 6 or 7 different rules. And we worked out the oxidation state of an element in a compound or an ion from the formula. Did a few examples of that as well. So we're done. I think we covered off all those learning objectives. Hopefully you've understood them. And in any case, I'll see you in the next video lesson.